Hey everyone, thanks for your attention for the conference and your attention for this research. My name is Yutian. I'm with the University of Vigo in Spain, in Galicia, Spain. Today I'm going to talk about the research in our group about modeling of Doppler effect in photonic integrated FMCW LiDAR system. The motivation of this research is to simulate the LiDAR system with moving target and numerical interconnects. The Doppler effect has to be taken into consideration. Unfortunately, the numerical interconnect can only simulate linear systems. That means parameters such as the target speed and waveguide length cannot change during the simulation time, which is needed if we want to simulate the Doppler effect. This research aimed to build a comprehensive Doppler LiDAR model in numerical interconnect to aid the design of such system and testing of various LiDAR configurations. Now I'm going to explain the methodology I used in this experiment. The picture on the right shows the system diagram of a typical FMCW LiDAR. It consists of a tunable laser source, of which the frequency is tuned by a triangular waveform. The modulated light goes into a coupler, which split the light into two passes, the RO path and the delay line path, which simulate the target reflectance. The light from the two paths is then recombined by an optical coupler, and the B signal is detected by a balance photodetector. An oscilloscope and a electrical spectrum analyzer are used to generate the waveform and spectrogram. Because the laser light is modulated by a triangular waveform, the light coming from the local oscillator and delay line will have a slightly different frequency, which depends on the target distance. If the target is moving towards or away from the laser source, the reflected signal will have a higher or lower relative frequency. This is the basic working principle of FMCW LiDAR system. Now, why is it difficult to simulate a system in numerical interconnect? It is because numerical interconnect can only be used to simulate a linear system, which means the parameters such as the speed of light and delay line length is unchangeable during one simulation. In order to solve this problem, the simulation is sliced into multiple segments in time domain, with each time domain have different delay line lengths. All the simulations are ran individually and the sliced time domain signals are recombined to obtain the Doppler waveform spectrum. The precise procedure is shown on the picture on the left. Now I'm going to start talking about the simulation setup, specifically for the laser source. The picture on the left shows you the laser source part of the simulation in numerical interconnect. It includes several components: the ideal laser source and monitors, the isolators, noise adders, because this is a perfect laser source. We do not have noise in the simulation, and if we want to make it more realistic, we need to add noise. The power and the power attenuator for simulating the coupling loss. The setup for this laser, it can be tuned for 500 megahertz. The frequency tuning range is 500 megahertz, and the modulation period is 3000 nanoseconds. The picture on the right shows you the spectrum of the laser for t equals to 0 nanoseconds and t equals to 1500 nanoseconds respectively. And the laser is tuned by a triangular waveform, so it's going from 1550 nanometer to 1550 nanometer plus 500 megahertz equal of wavelength. The picture on the bottom shows you the spectrum. Shows you the power versus time of these laser. Because we're having a perfect laser source, you don't see residual amplitude modulation in this case. Next, I will talk about the delay line and local oscillator part of the system. Here we have a splitter that splits the power into two paths. One serves as a local oscillator path that directly go to the second coupler, and the other one goes first to a waveguides. This is to simulate when light travel into free space, hits the target, mirror target, and comes back through the same path. And here we have a target distance of 50 meters, and then hits optical power attenuator. This is used to add optical loss during free space propagation. And in the end, the signal will be collected by two monitors here to ensure that two peaks will be seen. The third part, I'll talk about a simulation setup for balance detection and signal analysis. Here we have two photodiodes, one subtractor and one combiner to simulate the balance photodetection. Here we have a stripped laser source. This is used to later combine the sliced data. And I have a noise adder here because we cannot simulate electronic noise in this simulation. And this is to increase the reliability of the simulation. And in the end, I will talk about a simulation setup for the interconnect routes. The sampling rate for this simulation is set up to be 500 MHz. Simulation time is 3,000 nanoseconds. The number of samples is 30,000. Temperature is 300 K. The time segment for each slice is 2 nanoseconds, which means the change of waveguide length per slicing is about 0.6 meters. So for all the sliced simulation, the waveguide's length difference will be 0.6 meters. So yes. Here I will start talking about the result of the simulation. Here's the laser setup. For this particular simulation, we have a laser frequency deviation of 500 MHz, modulation period of 3000 nanoseconds, target distance of 100 meters, and target relative velocity of 36 meters per second. On the right, you can see the spectrum extracted from the oscilloscope. We have first this part, which is the time needed for the light to travel through the delay line. Here the light start recombining and we will see the rising edge, and here we see the falling edge. And on the bottom you will see the spectrum, which clearly shows the rising edge peak and the dropping edge peak. Using the spectrum data, we can calculate the target distance to be around 100.0368 meter, and the target velocity to be 36.0337 meter per second, which is very close to our setting. We tested this model with various LiDAR configurations, which is given in the table 1. Configuration 1, we have 3000 nanoseconds of modulation period. Configuration 2, we have 1500 nanosecond of modulation period, and configuration 3 we have 400 nanosecond of modulation period. This corresponds to different working distance. The first one is 100 to 60 meters when LiDAR, we assume the LiDAR is working from 100 meter to 60 meter. The second one is 60 to 15, and the third one is less than 50 meters. On the bottom two lines you can see the maximum and minimum target distance with the setting. The two picture here displays the simulation results. The blue dot is the measured distance. The green line displays the minimum working distance for each configuration, and the dash green line illustrates the maximum working distance for each configuration. The red line indicates the theoretical or the set target distance, and we can see here for the distance measurements, all the blue dots are match very well with the theoretical distance, except when the distance go beyond the measurement limits, go beyond the working distance limits. Here you can see the same goes as well for the target speed measurements, except for configuration 1, when the distance is very large and speed is very high, when the distance is very small, speed is very high, we see a lot of oscillations here. The distance calculation for the three configurations gives standard deviation of 0.3616 meter, which is acceptable. At the conclusion of this research, we have built a comprehensive LiDAR model capable of simulating Doppler effect, and 3 different LiDAR configurations functioning at different work distance are tested. With a proper estimation of the optical loss during propagation, coupling, together with a proper tunable laser model, we should be able to use this LiDAR model to estimate the performance of a LiDAR system with a moving target, and this will be very helpful for our future design of a photonic integrated LiDAR system on chip. And that's all. Thank you very much.